All right, welcome everyone. It's a pleasure to introduce you today Mariya Lyubenova. She's a close collaborator. She graduated in Munich at ISO with Harald Kunstner and David Silva, testing near-infrared models on global clusters and early type galaxies with some of the best symphony data around, IFU data. Then she moved to Heidelberg to work with this guy here, with Glenn van de Ven. And she started working on the dynamics and kinematics and dynamics of galaxies in the CALIFA survey. And then she moved to Groningen with Scott Traeger, who's also here, and became the lead scientist for the X-Shooter project, which is a stellar library using the X-Shooter instrument at the VLT, which is in fact the reason we are here this week. She's here this week, because we have a small meeting. So today she's going to give you a flavor of both things, and welcome.
Okay, thank you very much. It's a pleasure to be back here in the IAC. We've had a CALIFA busy week several years ago, which I immensely enjoyed. So when it came the time to make our next XSL busy week, it was, I think I did not need much time to convince Jesus to make a proposal for being here. So you've seen my talk was advertised for the interplay between baryons and dark matter in galaxies, but I first briefly wanted to give a very short introduction to what XSL is. So because we're preparing a data release very soon, and several of you most likely will be interested into using that. So XSL stands for the X-Shooter Spectral Library, and if you need to remember one thing about it, that this is a moderate resolution library containing about 700 unique stars. So this was a large program conducted in two phases. We first had a pilot program to test the observing strategy and data reduction, and later on we've continued with a large program which carried over 4 periods, and all of that was completed by the end of 2013. Observations with some more carried over later. So wrong direction. So this is the currently composed team. So it's a very diverse team encompassing almost 20 researchers in 8 institutes in 7 countries in several continents. And this week we're very lucky to have here all our PIs, even in the room, moreover, more or less. And so we're a mixed bag of expertises, but mainly in stellar population modeling. So this is what is our primary science goal, actually. So to develop a stellar spectral library which covers a wide spectral window for use in stellar population studies later on. And we aim, because X-Shooter is an instrument which simultaneously covers from about 300 nanometers in the UV to the almost 2.5 micrometers in the near infrared. This long baseline will allow us to study various kinds of astrophysical objects, and most importantly prepare us for the future observing facilities as well as current instrumentation. What we will provide to the end user, it's baseline spectra for studies of individual stellar types, so one can do a lot of stellar astrophysics, test bench for theoretical stellar libraries, and very important templates for kinematic studies of stellar system. And here we hope also to be able to make happy the exoplanet community as well, not only for global cluster studies or galaxies, but also to find very small velocity offsets. Is XSL the perfect stellar library? So if one asks what a perfect stellar library would have, so lots of stars covering all stellar evolutionary phases for all kind of conceivable stellar compositions of a stellar system, to have an excellent flux and wavelength calibration, so we can really rely on what we are mixing after that in a model, and a very broad wavelength coverage. And of course, all this should be done at once, observed at the same time, because several stellar phases contribute differently in the different phases of their life in different wavelengths. So in that respect, we're quite comfortable saying that we're fulfilling these requirements, and so we are covering as much as possible of the Hertzsprung crystal diagram, and we've given a spatial attention to cool stars, which were lacking in previous libraries. and we have significant fraction of galactic bulge giants to cover metal-rich stars, and we also aim to have as much as possible overlap between existing libraries, so to be able to compare between the other. So this is our atmospheric Hertzsprung crystal diagram with atmospheric parameters. And so this is a region which was previously sparsely populated in previous libraries. And so we will also get in future extensions of the library good coverage here at hot temperatures. It is important to remember that XSL is not a complete sample in a statistical sense, but it is complete in what is being observable from our location in space. So in terms of observations, so we have high-resolution spectra, moderate resolution spectra, apologies, in these three arms observed in with slightly variable slit weights, resulting us of total resolving power of around 10,000. And we also have wide slit observations, which we use for flux loss corrections of our stars, which we most likely will also release later on, so lower resolution spectrum. The current status of the library, so all observations were completed already 2 years ago, and we did the final count, and we have 679 unique stars observed and almost completely reduced by now. And several of these stars have been have repeated observations, many of them because they are variable stars and we wanted to be that, others because they had different fluxes in depending on the different arms, so they were having different exposure times to adjust to have at the end good coverage, good signal to noise throughout this very long wavelength range. We had already once a data release about 2 years ago, again, the DR1, which contains the UVB and visible spectra from the pilot program. And this contains about 250 spectra of around 230 unique stars. And we have a dedicated web service that all of you can access and your queries there. So this is how, with some basic statistics, what kind of stars were included in the first data release. So quite a lot of M stars. So this was we aimed at this pilot program to explore the feasibility of observing and reducing consistently cool stars, which were lacking before. And one can select so far in a few ways only. But for example, one can look for the B-type stars, and then one gets a complete list of what we have, and by clicking on one of these spectra, one can see, have a visualization, and then download the spectrum. And so I really like this picture from our data release 1 paper from Yamping Tank, and Yamping is also here in this audience, so you can ask her questions about the data DR1 spectra. And so broad representations of stars from hot OJ stars to cool dwarfs, and we also paid a special attention to many carbon rich stars, to which we just had a paper released by Anaïs Gono, also a member of the IIC at the moment, a visitor at the IIC at the moment. So a bit about, that's my last slide, about XSL. So we are preparing now a future data release, our DR2, for sometimes in the middle of this year, and this will contain all good spectra. So all the pilot program spectra attaching to them near-infrared arm, and all the remaining spectra, the large program, which were many more in numbers. So we'll all the spectra put to rest frames, so directly for one to download and use. We will have improved telluric correction with respect to the pilot program, to the data release 1, and improve flux calibration. And also what we will have now is a quality assurance model, which will have for every spectrum and arm detailed quality control information, what this spectrum is good for, so you as users can have a look at there and decide whether a given spectrum is usable for your science case or not. And so this is our website, and this is where all these things will become available. And so here I will stop with the XSL, so if you have urgent questions, you can ask now or later on, or to any of the XSL members here while we're during that week. Okay, so moving to the other talk. Good, now completely switching topic, moving to Galaxies. Now seeing the pile here of all these folders that you have to sign for the students, maybe they should get the 2 signatures today with having 2 talks. Okay, so CALIFA is another large program in which I was very happy to be part of. This project is more or less finished in terms of being released to the community. So we just had about a month ago our data release 3, where we gave to the community all galaxies observed so far and reduced. So if you have to remember a few things for what CALIFA can do for you, and these are its 3 major strengths. So that this is a survey of galaxies which has no morphological bias. So this is an improvement comparing to the pilot attempts by the Sauron team and Atlas 3D teams, which contained early type galaxies only. So here we're covering all kind of galaxies. So this is our color magnitude diagram of observed objects at some point. The second thing is that it is representative in a broad mass range. So here you can see our luminosity function, and the vertical dash lines indicate our completeness limits, and from -19 to -23 in absolute R band magnitude, and in stellar masses this corresponds to log of stellar mass 9.4 to 11.4. And the third thing is that it is a statistically well-defined sample. So the black line here shows the SDSS luminosity function, and the blue symbols show the CALIFA main sample function. And you see that in the range where we are completely compatible with the SDSS luminosity function. So this means that for whatever kind of work you do with these galaxies, by applying simple volume corrections, you can get statistically defined answer of what you have been looking at. And we recently had a paper submitted describing the data, and it's already available on AstroPH because our website is also alive. So a bit of statistics, what is into our, what kind of galaxies you can find. So this is the distribution of morphological types. And the differences here between the colors is that its main sample is dark blue and extension samples are orange. So these extension samples are galaxies which were observed for particular science cases which could not be addressed with the main CALIFA sample. So, so these are additional galaxies which do not fall in the completeness, in the completeness of CALIFA. So these are additional ones. Yeah, distribution of stellar masses, and again, so here it is the mass ranges 9.4 to 11.4, where we have a very good coverage, and also a very we are complete in a statistical sense. This is because being famous to show on data release website. So this is how the CALIFA data release 3 website looks like. Brief illustration what kind of galaxies are available, and one can go and do a very simple query, either object or all the galaxies in the DR3, or you can select by location on the sky, or by redshift, or by magnitude, or Hubble type, barredness, merging, or isolated, and you can click the button and download 3 flavors of the data cube. One, it is a high resolution data cube in the blue wavelength range, about 4,000 angstroms, which is very useful for stellar kinematics, and that's what we have been using in our group. And the other one is the V5 low spectral resolution from about 4,000 angstroms to 7,000 a little bit, which is mainly useful for stellar population studies. And we also provide a combined data cube from the blue and from the low and the high spectral resolution cubes, smoothed of course to a homogeneous resolution, which solves certain problems with vignetting that we had with the instrument. So with that, I'm moving to how I've been using CALIFA in the last few years, and this is work that I have been doing in collaboration with Jesus and Glenn. And so from these original samples that were observed, we have selected 300 galaxies with excellent stellar kinematics. And this is the distribution of this pre-selection, this additional selection of galaxies. So with dark points, we have the original CALIFA sample, and with red points we have the kinematics 300 sample, and you see that it is in all respect similar to the previous one. So we consider also our 300 galaxy subsample statistically well defined with similar luminosity function as the CALIFA mother sample one. What is very important is that our stellar kinematics extends for 70% of the galaxies beyond about 2 active radii. So this is a significant improvement also with respect to previous surveys due to the large field of view of the instrument used, the PPAC instrument, and also the choice, the sample was selected to fit at least D25 inside the full field of view. So we are having good quality data much beyond the 1 effective radius, which is usually typically achieved with previous surveys. So this is a quick representation of what kind of stellar kinematic features we have in the galaxies that we are observing and analyzing in a very homogeneous way. So here are the usual boring elliptical with very little rotation, with a lot of random motions, so the typical slow rotating galaxy, moving to lenticular galaxies which have pronounced disk with a lot of rotation, but still a significant bulge, also exhibiting high velocity dispersion values, moving to pure disk systems with very little sigma, and also we have quite a lot of interacting samples, and that was Jorge Barrera Ballesteros, former PhD student of this institute, who made really interesting studies of the stellar kinematics of stellar and ionized gas kinematics of interacting galaxies. So with that part, so what has been my contribution further on is to do dynamical modeling of all these galaxies, and again, not paying any attention to whether it's a spiral or an elliptical galaxy, just in a very homogeneous way. And so here is a brief description how we are doing the dynamical modeling. So we use the light of the galaxy to parameterize the gravitational potential, and then we use the kinematics fields to derive to make a dynamical model. And we're using 3 different approaches that in our team. So we're using genes-based equations, so this is the work that I'll be talking about today. But there is also Ling Zhu, who is a postdoc in Heidelberg, who has been performing Schwarzschild orbit superposition modeling for these galaxies, and she now just, as we speak, obtains really exciting results. Unfortunately, I won't have time to cover that. And our most recent endeavor is dynamical models based on distribution functions. So this effort is led by Lorenzo Posti, who is a postdoc currently in the Kapteyn Institute in Groningen. And so this picture here illustrates the genes-based the genes-based model. So we combine the stellar velocity and velocity dispersion fields into a second velocity moment observed, and we model that, and out of the dynamical model we get the total enclosed mass inside a given radius. And as we've done this consistently for the galaxies of all Hubble types, of all stellar masses in our sample, we can start looking into astrophysical questions. And for example, one very popular question is reconciling the stellar halo to mass relation to observed galaxies. And so here, this is how, when we look at the total to stellar mass ratio in our galaxies, and this is what kind of, I would say, weird behavior we observe. Because, so if galaxies contained only stars, the total to stellar mass ratio would be 1, and 1 or here or there, depending on the initial mass function, which is assumed for the stellar population-based masses. However, here we see that this is valid only for galaxies around between 10 to the 10 and 10 to the 11, so more or less Milky Way type systems. And we see two departures, both at the high mass end, where galaxies move, show this significant deviation, and also at the low mass end, where we have this deviation is even higher. And pay attention that this is a log scale, so this galaxy here has a ratio of 40 to 50 of the total to stellar mass. So there is huge amount of mass, an invisible mass that we are not seeing. So I'll first concentrate now in the talk into these low mass late type spiral galaxies. And so these, you see here already from the way the plot is presented that it actually matters what kind of initial mass function you're going to assume when you're doing your stellar population based stellar mass estimate. And we know that galaxies over the last few years are suspected more and more to have a non-standard and very variable initial mass function. And however, such claims are made and observed so far only in early type galaxies, in giant ellipticals, and nothing so for late type galaxies, for spirals, we have no evidence so far that the IMF is varying. And actually, it's quite the opposite. Wherever we look around, we see quite a constant IMF. So what we are left to consider then that this really high upturn is due to very high dark matter fractions, even inside the effective radius for which we're plotting this ratio here, which is something not unexpected because we know that local group dwarf galaxies, they're even more dark matter dominated, so there would be lying somewhere here, or I don't remember where was the last, they can have total to stellar mass ratios of the order of 100 and more. And however, there is something important to pay attention here, because these are low mass spirals, so they can have as much gas as stars in them. And we have tried to correct that at the moment only with using an empirical prescription based on the stellar mass and their H1 content, H1 and H2 content. And so this is what these arrows illustrate. So in trying to form here not a total stellar mass, but more like a baryonic mass versus the dynamical versus baryonic mass fraction. And of course, this helps a bit, bringing back the galaxies down closer to the 1-to-1, but by far not. So let's look at one of these outliers. Is there anything specific about them? And not really, I would say. It's a normal SE galaxy with quite a normal kinematic field, with exception of that. So it exhibits quite a lot of rotation, but it has also a very high velocity dispersion, especially in the outer beams. And first, seeing these guys, we thought, oh, this must be some problem with our method, and we're making some error in the stellar kinematics. But we have done several tests, like Jesus, who has been scratching his head forever to try to find answers. And so we are left with the conviction that these guys are real, and this is what we are obtaining. And more or less, this high sigma here, it is in the very outer parts, but these models that I'm talking about here are only constrained within the one effective radius. So also within the effective radius, the velocity dispersion is very, very high. And the good thing is that for several of these galaxies, they have considerable gas amounts, and last year there was a survey conducted with CARMA, the CO radio facility in the US, just a few days before it was closed effectively. So we managed to observe about 130 galaxies. And so this is a preliminary snapshot of their velocity fields. And this is the overlap that we're having with the CALIFA 300 sample. So all the galaxies with diamonds are in the edge sample as well. This outlying galaxy that I was showing before, unfortunately, doesn't have very good CO detection, but many others do have. So here, this is one of the galaxies which is curiously below the 1-to-1 line, and the other so we can investigate special cases. And the good thing of having CO observations is that the CO gas is assumed to be in a thin plane, so it is very easily to from the rotation curve, from the circular velocity, to obtain a total mass of the galaxy. And this is how the relation between the circular velocity, which directly translates to the total mass of the galaxy, between the CO data and the GEANS modeling looks like. So the straight line here is the 1-to-1 relation, so this is not a fit, just 1-to-1. And all open symbols are galaxies with low signal-to-noise CO data and not very extended coverage. So to estimate the circular velocity at one effective radius, there needed to be extrapolation. So this explains why they're sitting so much further out. However, for the majority of the galaxies in the overlap, the two ways to estimate the rotation, the circular velocity, are lying very close to the 1-to-1 relation, which is actually very reassuring that we are doing quite well on the with respect to the dynamical mass estimates for our galaxies, because here we have two absolutely independent methods to constrain the total mass of the galaxy. So one is the cold CO gas, and the other one is the stellar kinematics from optical observations. And I'm looking forward for the paper. So this is work led by a PhD student in Heidelberg, Gigi Leung, and who is concentrated mainly into looking for differences and similarities between optical and CO velocity curves. So with that come, I cannot, I hope I've been convincing you that that we've taken all efforts to see whether it can something can go wrong with respect to our dynamical modeling, that this number is correct, and we have also taken a great care to check also whether the other number, the denominator of this ratio, the stellar mass, is correct. So here I'm presenting stellar masses based on the full spectrum fitting starlight method that has been used in CALIFA by a group in the Institute of Astrophysics in Granada. However, we have used several other methods to estimate our stellar masses using WISE photometry, near infrared based, and using full SED fitting from SDSS magnitudes, and we always find this shape consistently. So there are certain offsets, certain 0-point offsets between one or the other method, but in general this shape is very much preserved. So we are left to conclude that low mass spiral galaxies are heavily dark matter dominated inside effective radius. Yeah? No, absolutely not. We do not want to be burdened by something that we do not know. Moreover, here we are, when we do the dynamical model, we constrain inside the effective radius only. And first, for elliptical galaxies, this is known, so I'm just moving now to elliptical galaxies. So this is known that there is a very small contribution of the order of 10% inside the effective radius. For spiral galaxies, we've assumed that it's going to be similar. Now we see that it's not actually. However, we do not want to make assumption on the dark matter halo profile, but we want to derive it backwards. So because with this data, we also have for several of the galaxies coverage to 3 to 4 effective radii. So from there, we can already make a dynamical model which includes several dark matter halo profiles and try to reconcile that. And this is a work that Ling Zhu is doing with the Schwarzschild modeling, because the GEANS modeling is not very flexible. There are way too many degeneracies. No, nothing for this model. Yeah. Okay, so with that said, I'm moving to the high mass and Furley type galaxies here on the other side of this total to stellar mass fractions. These galaxies, which also have an upturn here, as already I briefly mentioned, that dark matter at these galaxy masses is expected to be around 10% only, and these are fractions. These are much higher fractions. So this is not. If you remove 10% of dark matter, then you're not going to bring suddenly the galaxies down here. So as I've said earlier. The initial mass function has been shown to vary in various ways in these galaxies. So maybe this is the issue here. Maybe we are not estimating the stellar mass correctly, and maybe we are using IMF function in an IMF which does not have enough heavy stars, and that's why we obtain a lighter mass, stellar mass. But when we talk about varying initial mass function, there is a big problem because usually every researcher has a different idea what varies in an initial mass function. So, and here this is one of the most complicated plots which I've seen for initial mass functions, various ones, and you see that all of them are different. Okay, they have more or less the same shape that, yeah, okay, there are very few low mass stars, high mass stars, and also the maximum of around one solar mass, and then again either going down or going up for lower mass stars. But it's a big mess, and one can choose any of these stellar initial mass functions, make a stellar population model, and derive stellar masses with them. And Mm-hmm. Okay, interesting. At 0.5, so it stopped like here. And it's an extrapolation, yeah. Okay, yeah. I've been planning actually to make an updated version because there are more IMFs proposed, because this one stops at about 2003 with the Chabria IMF, and there have been more IMFs proposed later on. And this is something that we'll be discussing now in my next plot. So, but when we talk about varying IMF function, what does it vary? And with the dynamical models that we are doing, we can actually make a very simple test and check whether and check for a specific kind of a variation. So this is the shape of the IMF that we have chosen to explore. So the stellar population-based method to study variable IMFs basically is sensitive to the ratio of dwarfs to giant stars. So what we have in the spectra of galaxies we can decipher at the moment, this is only this ratio. And so here what I've been plotting is predictions for the mass to light ratio for a single stellar population with that metallicity and age for two different IMF shapes, and this is from the Miles models predictions. So one was for the one is the so-called single power law or unimodal, and the other one is double power law or bimodal IMF. And you see that at any given dwarf to giant ratio, the mass to light ratio can be significantly different from one to the other, depending from the shape of the IMF in which this dwarf to giant ratio is distributed later on. So the test that we've been doing with the CALIFA dynamical models and stellar populations analysis is very simple, that the stellar mass to light ratio cannot be larger than the dynamical one. As simple as that. Because the dynamical mass to light ratio contains everything in it, so it contains dark matter, because we do not subtract dark matter before, we do not make any assumption on the dark matter halo, and it might contain gas contribution, but we also, these giant elliptical galaxies have negligible fractions to zero gas contribution, so we couldn't care less about that as well. So and then, of course, the majority of the signal in the dynamical mass light ratio will be coming from the stars themselves. And when we are doing the dynamical model and the stellar analysis in the same light regime, so looking at the same stars, then we are measuring apples with apples. And so this is our diagnostic plot. We have a huge triangle here which is forbidden. Like there cannot be a galaxy living in that area if we trust the dynamical mass-to-light ratio. So this is yet another cut in our sample of 27 elliptical galaxies with at the highest mass range 10 to the 12 in stellar mass. And so this cut was mainly needed because of the way we do our stellar population analysis. So features sensitive to the dwarf to giant ratio, namely the titanium oxide, falls in, at the redshift of CALIFA galaxies into unpleasant telluric absorption region. So these galaxies are in a very narrow redshift range where this feature would be out of this region. And I'm sure the audience here is very familiar with this work developed here by Ignacio Martin Navarro, who left you about half a year ago to go for a postdoc in the US. And brief recap of the stellar dynamical analysis. So we perform a Jeans dynamical model exactly in the same way as I described it before, but on only elliptical galaxies. And here this model is constrained even more centrally, so only the Halfon RE. So in this plot, so the RE of these galaxies is around this outer isophot in both of them. So this is like half of that is in the very central parts. This choice was due for to be in a way to first assure very high signal to noise for stellar population analysis, but also to minimize even further the contribution from dark matter towards the center of the galaxy. So even this 10%, maybe we will be getting even less contribution from dark matter. So we allow the velocity anisotropy to vary in these galaxies, in this modeling, but we kept it constant over the galaxy, and we made a mass follows light assumption, so constant mass to light ratio throughout the complete galaxy. And we are aware that this is one limitation of our approach. However, we've explored actually by allowing the mass-light ratio slope being in the dynamical model being a free parameter, and we didn't see that this was improving the fit. And also, from stellar population-based studies, we have no reason to believe that these giant elliptical galaxies will have radially varying mass-to-light ratios, stellar mass-to-light ratios. So thus we concluded that our choice of constant mass-to-light ratio should be robust. And in that way, we obtain the mass-to-light ratio is constrained inside the effective light, half the effective light radius, a total one, which comes from all contributors to the dynamic stars, gas, and dark matter. Gas is negligible. These are giant elliptical galaxies. If they have any, it's for majority of them, and they actually have zero gas detection so far. The stellar population analysis, I suppose, not much needed to explain here. It's a local expertise of yours. We've used the integrated spectrum inside the half-RE, so exactly the spectrum that we used to make the dynamical model, now this time integrated into one single spectrum, measuring the line strengths of H-beta, which is an H indicator, magnesium iron, which is a metallicity indicator, and the titanium oxide, which is a dwarf to giants ratio indicator, so an index sensitive to the IMF. All this work was done in the framework of the Milles models. And with that, we obtained the stellar mass-to-light ratio inside the same aperture as we use for the dynamical model. So we are comparing again apples with apples. Why we chose the Milles models? Because they are very useful with that they allow at the moment very easily to plug in different shapes of the IMF and different variations. So we have studied two particular cases. So the single power law shape, so this is the straight line or the so-called unimodal, and this is very close to the salpeter line. And when we let it vary, so it has a variable slope gamma, so this is how it varies. So these are two representations. The the solid and dashed line. And the other shape that we explored was the so-called double polar law or bimodal, which has a variable high mass and slope, gamma b here, and the solid line is very close to the Krupa or Chabrier IMF. So this is where our galaxies sit on our diagnostic plot with dynamical mass to light ratio versus stellar 1. And here, for the case where we use a single power law IMF shape, and here we've used actually two ways to determine the mass to light ratio of the galaxies. So the lilac symbols are only from H beta and magnesium iron lines. So we do not include any titanium oxide, so no sensitivity to the dwarf to giant ratio in the galaxies. And we assume a fixed salpeter IMF shape for all of them. And this is where they lay. So these galaxies, they are all old and dead and with all above 8 gigayears and all solar and higher metallicity. So this is explicable why their stellar mass to light ratio is in such a narrow range, you see. And but their dynamical mass to light ratios exhibit a very big range, like a factor of 3 difference from one to the other side. So if we were to believe that this is the right way to estimate a mass to light ratio of giant galaxy and the salpeter IMF would be the correct one, this would imply huge dark matter fraction into these galaxies, because anything else contributes what else can be to make the dynamical mass to light ratio so big. So this is dark matter, and this has not been seen by other studies before. So as I said, it's usually 10%, not 3 times more. So when we included all indices, so now also including the dwarf to giant sensitive index, and we allowed the high mass and slope, no, not the high mass and, so the slope of this single power law shape, like here it is for reference, to vary, then this is where our points landed. So the horizontal lines just connect the same galaxies for guiding the eye where they move. And we see that 75% of the galaxies actually end up in the forbidden region. So this way of estimating the stellar mass to light ratio predicts more mass. That's what we are observing dynamically. So, this is unphysical. So we cannot have more stars than stars plus dark matter. The situation improves significantly when we use the double power law shape. So again, we've done the same experiment without including the titanium oxide feature and having a fixed Krupa IMF shape, which is a double power law shape. And again, we obtain the same narrow range of properties, mass to light ratios of the galaxies, and again, the same need of a huge dark matter fraction, if this were true. But when we included all the indices and we let the high mass and slope of this function to vary, so with steeper slope indicating more, in general, more low mass stars or dark remnants in the population. And then we see that the galaxies move out of this forbidden region. And actually about 95% are within 1 sigma compatible, being out of the forbidden region. There are still departures from that, but I'm going to come later to that point. So from that test, we actually conclude that the single power low IMF shape is disfavored in these galaxies. Of course, we do not claim that the double power low IMF shape is the right one, the correct one, or so. There might be many out there, but we say that this one, single power law with a variable slope, this leads to unphysical stellar mass to light ratios. So, so this brings me to the next part and the last part of my talk, where I will look into whether stellar populations and dynamics give you a consistent result about the variation of the IMF in general, because you saw, like all these galaxies so far, each one of them has a different slope of the IMF. So No, you have not seen that, but yes, so we allow this here, and the slope of variation that we are, the range of slope variations is rather large. We'll come to that a bit later. So, and in general, when we're talking about a variable IMF function, so we need to have consistency checks between different methods. And so this was a very nice study performed by Russell Smith 2 years ago, based on literature data, taking the Atlas 3D result. So this is the famous Nature paper saying that the IMF varies in giant elliptical galaxies with mainly with their velocity dispersion. And the other very famous result in that respect, the Conroy and Van Dokkum, from which are looking from stellar population point of view, looking at the indices of the galaxies and finding same variation, but this and interpreting that this variation is driven by the chemistry of the galaxy. And of course, first question to answer is, are the dynamical mass-to-light ratios and stellar populations based mass-to-light ratios consistent with each other? And he plotted these two relation, and he found indeed quite a good correlation between them. However, here we have to pay very much attention that this correlation might be due to underlying stellar population properties, and which first need to be taken out before we compare any dynamics and stellar population-based evidence for IMF variation. And this is where we come to this infamous or famous alpha or beta or Imf Mismatch Parameter, which is basically a mass excess parameter, so which tells us if a stellar population had as much, it had a chosen reference IMF function, it will have alpha of 1, so all the galaxies will be clustering at this point here, 1, 1. And and if the galaxy has more mass, either from the stars or from other contributors to the dynamics, like dark matter, then the galaxy would be moving here or there into these higher regions. And so this is how this literature comparison looked like between Atlas 3D and Conroy and Van Dokkum. And you see there is no correlation. This is the correlation coefficient, completely consistent with zero correlation between these two evidences for a variable initial mass function. Quite interestingly, what the red cross shows here, it is the average for the sample, and this lays on the one-to-one relation, but of course when we have a cloud of non-correlated points, it's very likely that the median will be somewhere in the middle, and so this cannot be taken as a serious confirmation that we have a consistency check between these two efforts. And however, in this comparison, there are quite a lot of factors which the author could not control, because this was not his own data, but other studies. And one, for example, was that, so these are the same galaxies, but observed with different setups, different instruments, and also in very different apertures. So the dynamical mass-to-light ratio comes from almost 1 effective radius aperture, and the stellar population one comes from 1/8 of an effective radius. And if these galaxies are to have gradients in the mass-to-light ratios, this all would be erased. And another difference is into the adopted IMF shapes for one or the other, and for the reference points that they're using. And he made an attempt, so these are what the blue points are, the blue symbols, the blue lines are pointing where galaxies are moving when a consistent reference is used for both these samples, but of course this didn't help at all. So with CALIFA we can do much more on that respect. So this is how our comparison between dynamics and stellar population based evidence for IMF variation looks like. So we have exactly the same aperture, exactly the same spatial extent of the galaxies covered, so one worry is gone. And we are observing much stronger correlation here, and this is our probability of having no correlation, so only 4%. And the majority of the galaxies are indeed, first, they are here outside of the forbidden region, which it's not the case for half of the sample of Smith. So I'm not going to discuss why these galaxies are ending up there. There are many, many reasons why there can be. It can be from not an optimal choice of IMF and its variation from the stellar population point of view, but it can be also from the dynamics of no optimal dark matter profile assumption to be subtracted to obtain the dynamical evidence. So this is why actually, now coming back to the question of natural, before we have chosen actually not to do any assumptions here, because we see that it can lead to quite biased results later on if you make such a strong assumption in the very beginning and you by chance forget about it. So from this plot, what we see is that if all galaxies had the reference chosen group IMF, they would be here on this line, and we have basically almost nothing. And what I've illustrated here with colors is the fraction of stars below 0.5, so the dwarf to giant fraction in these galaxies, with the Milky Way value being around here, 0.3, so this symbol here, that is why it's also on the 1-to-1 line. And you see that the higher the dynamical mass excess is, which has nothing to do with the dwarf to giants ratio, by the way, because it is with the way we measure the dwarf to giant ratio, the higher the dwarf to giant ratio is, so the color gets more orange with an increasing with an increasing dynamical mismatch factor. So of course these departures here from the 1-to-1 line might be due to an increased fraction of dark matter, and this we are investigating now with the Schwarzschild dynamical model, where we do make we include various profile and see whether we'll be able to get better fits. But at the moment this test tells us that we obtain consistent result about the varying IMF between dynamics and stellar populations. And this is actually where I'd like to conclude. So my final slide about CALIFA. So the important thing to remember is that it provides a statistical view of the interplay of baryons and dark matter of galaxies. So with we are observing this interesting features in the stellar to the total to stellar mass to light ratios of galaxies, and we have found that low mass spiral galaxies are heavily dark matter dominated inside the effective radius. How much exactly? This is an ongoing work. Now, after we have also the CO data, we can estimate what is the precise amount of gas to include to the baryonic budget, so then later on we'll be able to actually, this plot being now only qualitative, to move and be quantitative and reconcile that properly with the stellar to halo mass relation. The moving to the high mass and galaxies, we can say that the single power law IMF shape is ruled out as an IMF for the stellar populations in these galaxies. And the last thing is that stellar populations and dynamics give us consistent result about the variation of the IMF in these giant galaxies. Thank you very much.
Questions?
Yeah, I was quite curious about the plot that you have on the corner, the top corner. I mean, the scatter is quite constant along the entire mass range that you are exploring. It's around a factor of 3.
Yep.
So I was wondering whether you have explored what is the reason behind that scatter. Is the size of the galaxies, the shape of the halo, is the rotation of the galaxy? So do you have any idea of why, I mean, what is the difference between the upper part of the
and the lower
envelope
part,
and the bottom envelope?
Yeah, we have no ideas at the moment for that. This is not something that we observe ourselves for the first time, and this is the range of this scatter, which also was seen in the disk mass survey. So Thomas Martinson has been working on that extensively, so we, as I said, we don't have yet information on the dark matter halo shapes, of these galaxies. But this is something that we are curious ourselves to see what is the reason, why a galaxy is here or there on one side. Because at the moment, like with the simple morphology, this doesn't work at all. There is no information from that, but the rest we don't know yet.
Hi, very nice thing. So I was wondering if you also somehow exclude or include the environmental effect, the dynamical environmental effect when you calculate the dynamical mass.
Mm-hmm.
So are all these CALIFA galaxies like field kind of galaxies, or are they also in the cluster of the galaxies? So do you consider kind of do you discriminate them or not?
Mm-hmm. Yeah, unfortunately, this is yet another unknown that we have in our work, and we do not have good estimates of the environment of these galaxies. And we need that for several other studies, for several other projects that we are doing, like the kinematic transformation of galaxies, and we just don't know that, unfortunately. And we know that some of them are in clusters, some of them are in rich clusters, some of them in fields, but it's not, we do not have consistently for all the galaxies this information.
More questions?
Hi. Yeah, I don't remember what the question was there, so I will not comment on that. But one question I had was about you had CO observations,
Yes?
which you used for getting the rotation curve. But haven't you used also maybe the ionized gas in the PPAC?
Mm-hmm. Yes, we did. Yeah, and we got consistent measures. So the thing is that with ionized gas, you cannot neglect also its velocity dispersion, and with the PPAC, it has the H alpha line being in the very red part. It has very low spectral resolution. So this is one technological problem that we're having, that we cannot use this one. But only using the only the velocity, the H alpha velocity fields, we got more or less consistent rotation curves with the stellar ones.
Okay.
But I'm not going to plot them on the line and say they're one-to-one, because there are effects unaccounted for.
Can I ask another one? About the dark matter in the in the early type galaxies, is it that strange? I mean, I know that most people would think that the factor of 4 more dark matter within half effective radius is out of the question. But still, if you believe that there is dark matter at all, why couldn't there be big ranges of the amount in a galaxy? I mean, why can't it be that in some galaxies there is 10% and in some there is 99% dark matter?
Mm-hmm. Yeah. Well, I think this comes already going back to cosmological formation of galaxies, and that big galaxies, they form from many subsequent mergers, so they keep on growing mass while the dark matter stays approximately constant or so. By doing retroactively our exercise, making a detailed account of the baryonic fraction in the galaxies, and by meaning of and getting like what we've been doing with the variable IMF, and then we obtain with when we subtract that from the dynamical mass estimated with the dynamical model, we again obtain this 10% without a priori assumption of what the dark matter would be doing there. So of course, yeah, that cannot be. This doesn't tell us that for all galaxies this would be true, but this is what we are seeing retroactively.
Okay, thanks.
I have difficulties to understand the position of this turn-up of the mass-to-light relation for the low-mass spiral galaxies, because as far as I know, the mass-to-light ratio in early type galaxies like NGC 205, 147, 185, this dwarf elliptical galaxies, this mass-to-light ratio is more like the other more massive elliptical, so it's around 2, 3, I don't know, something like that. And so either this is wrong, or I cannot understand why the ellipticals will be below. I can understand if they are above, but not below, because in the evolution they can lose some gas, but hardly decrease their mass to light. So,
So
there's something wrong in when I am thinking that the mass to light ratio of this around 10 to the 9 solar masses is more like the other ellipticals.
of the dwarfs, you mean, like that they will be located somewhere there?
yeah.
Yes, indeed, they're exactly there, and we've been studying that in a different project. And there it's quite an interesting story that maybe they have lost their dark matter halo actually from during interactions, and it is so. This is what is the explanation that we've been seeing at the moment. So that it is they did not lose that much of their stars, but the dark matter, and that's what it drives their total to stellar mass to light ratio down. You're not convinced in that? Okay, well, we can talk about that later on, because it's an interesting topic, but because there are various scenarios proposed for the transformation mechanisms of how these, for example, how these similar mass spirals can be the progenitors of dwarf ellipticals, and whether this is harassment or tidal stripping, and this is one effect that one can expect, that they will indeed reconcile with the other because of losing dark matter halo.
More questions? Mike.
Thanks, a nice talk, Mariya. I was wondering, what's the role of black holes in this, particularly in the most massive, the giant ellipticals?
Forget about them.
So, for example, so they're dark matter, right?
So
They're dark, right?
Yes.
But you'd measure that as a mass within
yeah.
the central region. So, what contribution would a supermassive black hole have to your dark matter fractions?
So the point is that the supermassive black holes, they have a very little influence on the kinematics, only inside their sphere of influence, which is completely inaccessible at this redshift range, and with because our spatial resolution is of the order of half a kiloparsec with these galaxies, so it is completely inaccessible.
And also the models where, for example, if you have binary black holes which create cores in massive galaxies, so redistributing the stellar light, is that in any way affecting your measurements? Are you so far out you're insensitive to that?
I think we will be also insensitive to that, but I think these are just much smaller spatial scale effects.
Okay.
More questions? Well, if there are none, let's thank Mariya again for the nice
Thank you.
presentation. And there should be coffee for us waiting downstairs in the library.